Now let's look at the geometry involved. So I've simplified my diagram a great deal. On the left-hand side, you see my two slits as represented by tiny little dots. There's a slit on the top where my hand is, slit on the bottom, and they're separated by a distance d. The red lines indicate how far the waves have to travel from the lower slit, as represented by d1, and similarly d2 is how far they have to travel from the top slit to a point P. Furthermore, let's assume that on the right-hand side, we see an interference pattern of bright and dark spots as represented graphically by what we see here. So our most intense wave is right in the dead center, our most intense antinode, and then we've got a node, an antinode, a node, and another antinode. So point P lies at the second antinode away from the center. We've already discussed that at the first antinode, the lower wave will have traveled one additional wavelength further than the top wave, so that they're still in sync and they get constructive interference. And if we're at the second antinode, the wave at the bottom will have traveled two wavelengths further. So let's label that on our diagram. So we see from the diagram I've labeled 1 lambda for the first antinode, 2 lambda for the second, 3 lambda for the third, and because it's symmetrical on the top and the bottom, I have the same numbers down below. Now, the number that's in front of lambda, we can just call that m. So if we represent this by m lambda, we see that the top one, m can be 1, 2, 3, all the way up, whole number integers. Now let's look at our dark spots, or our nodes. If the wave hit where my hand is located right here, the bottom wave will have traveled 1/2 a wavelength further than the top and will be exactly out of sync by half a wavelength, and you'll get destructive interference. If we move to the next node, it would have traveled 1.5 wavelengths further, 2.5 wavelengths further, etc. Let's label these on the bottom in blue. So if we're looking for locations of nodes or dark spots, we're going to have this factor of 1/2 in there. So we can simplify this as well in terms of an integer or a whole number. So for our nodes, we will write our equation as m plus 1/2 lambda. And in this case, m could be 0, 1, 2, 3, etc. It's very intuitive. Notice that m could be 0 because the first one's 1/2. So 0 plus 1/2 gives me my first node. Whereas at the top, if I put m as 0, we're at the center, and it doesn't really help us mathematically. So that's the first step. Second step is we actually look at some geometry down below, and it requires a bit of an assumption. The assumption is that this distance to the screen, which we're calling L here, L is the distance from the screen all the way back to the double slits. If that's very, very, very large compared to D, then we can assume that these two red lines are basically parallel when we're back at the double slit end. Now with this assumption, if I construct a right triangle where D is the hypotenuse, then I can basically say that this little side right here where my hand is the extra distance that the bottom wave has to travel. And if that extra distance is a whole number of wavelengths, we get constructive interference. If it's a half a number of wavelengths further, we get destructive interference. So it all hinges on these angles and some really basic formulas. The angle theta is right here where this top vertex is. Because of our assumption, it's the same as this central angle here. And theta later on will be from the center line, right down the center to the middle in between the two slits, out to our location where we're looking at our node or our antinode. And we'll do a sample problem in a bit. So this little extra piece, which I'm going to circle in blue, now if we're looking at an antinode, this little extra distance here that the bottom wave has to travel is a whole number of wavelengths further than the top. So this little extra distance on our equation will be m lambda if we're looking at antinodes. Now if we look at the triangle we constructed where D is the hypotenuse, theta is the upper vertex, and this little piece, this little m lambda piece, is opposite to the angle. So we can say that sine theta is opposite over hypotenuse. And if we rearrange this formula, we get our double slit equation that says d sine theta is m lambda. That's our equation that'll help us locate the positions of all the antinodes on the screen. And we can combine it with some basic geometry to actually find these actual values in meters. And we'll look at a sample problem in a second. Now keep in mind, if we wanted to find the nodes, the equation is almost identical, except that little extra distance will be m plus a half lambda. So in the next tutorial, we'll do a sample problem and see how this all works.